Remember earlier in the year we looked at relations and functions. A relation being a set of x and y values. That's a relation. And a function is a relation which has only one y value for each x value. The graph of a function can be crossed once by a vertical line, and that's what we call the vertical line test. Okay, so let's revisit that again. The key statement there is has only one y value for each x value. So if we look here, it doesn't matter which x value I choose. If I draw a vertical line, it doesn't matter which x value I choose, I'm only crossing the graph once. So each x value's only got one y value. So wherever I go down here, we've seen this before, the vertical line test, it passes that test because we're only meeting the graph at one spot. So each x has only one y value. What sort of graph doesn't fit that? Well, we've seen before that, for example, these sorts of things. If we did the vertical line test there, it would fail straight away because x's would have two y's in that case. And of course, what we learned earlier in the year is that circles are not a function either. Okay, if we draw a circle, that doesn't pass the vertical line test either, and we easily cross through 2 points there. So that's the vertical line test. State whether or not each of the following is a function by using the vertical line test. Let's start here with x plus 1 squared minus 3, this one here. There's the graph of it. So it's x minus 1 squared, y equals x minus 1 squared. What was it again? No, sorry, x plus 1 squared minus 3. And of course we know that the plus 1 there in the brackets, that plus 1 moves our graph one place to the left. Okay, and we know that the minus 3 there moves the graph 3 places down. So it would move it down 3 places. So you can see that there. Anyway, does it pass the vertical line test? Of course it does. Let's get our vertical line happening again. Doesn't matter where or what x value I choose, I'm only passing the graph at 1 point. So for each x there's one and only one y. So it passes the vertical line test there. Second graph is x squared plus y squared equals 1. This graph here. Sorry, this graph here. And that's a circle. It's got a radius of 1. And as I pointed out before, that doesn't pass the vertical line test. As you can see, x values have got two corresponding y values there. So it is not a function. Last one is the hyperbola I've got here. Here it is. Y equals 4 over x minus 2 plus 1. We've got a dilation factor here. We've got a shift 2 places to the right and 1 place up for that hyperbola. Something like that. Let's have a look here at the vertical line test. Certainly, whatever point I choose on the graph, it's only passing it once. It's an asymptote there, but that doesn't matter. It's still a function, and it passes the vertical line test. For the following function, next question, sketch on the same set of axes the graph of the function, its inverse, and the line y equals x. State the domain and the range for the function and its inverse. Alright, let's have a look at that. Let's have a look at the inverse first of all. We've got two methods here. One method we learnt earlier in the year, and with that method, remember that what you do is you swap x and y over it. You can see there, just change those arrows just for a moment. It's better. You swap x and y over. See, I've done that. Y has become x, x has become y. And what you do then, from then on, you aim to get y by itself. So you can see in the next line, going from here to here, what I've done is I've undone it from the log form. Okay, remember you can, toggle, if you like, between log and exponential form. E to the power of x equals y plus 1. And See, that's what I've done there in the next line. And then to get y by itself, it's just simply a matter of taking the plus 1 over. So y would equal e to the power of x minus 1. Now, we can do this on our graphics calculator. We swap x and y over first. So solve x equals log y plus 1 base e, or ln y plus 1, and solve for y. So what you're saying is, okay, we've swapped x and y over. There it is. And then find me y after I've done that. And that's the process we just did. And you can see your answer here for the inverse is the same. So what I've done in the next graph is I've, on my graphing program, you can do this in your graphics calculator, I have graphed the original. Okay, so the original, remember, was log x plus 1. And the log graph is this one here. So y equals x plus 1. It's the purple graph. Its inverse has also been logged, okay, graphed, and that's, we just worked that out, that's e to the power of x minus 1, so y equals e to the power of x minus 1, that's the orange graph, and the graph also y equals x. We pointed out on an earlier video that the inverse is a reflection of the original about that line of y equals x. You can see here, pointed this out before, you can see that reflection. If I draw arrows, that reflection becomes apparent. There we go. Now, we're asked to find the domain and the range of both of those graphs. So let's look first of all at the domain and range of log x plus 1 to the base c. Well, we know that's a log graph that's been shifted one place to the left. So its domain, okay, is going to be, because one place to the left is negative 1 to infinity. Okay. Remember, negative 1 will be the vertical asymptote there. Its range is all real values. Looking at my other graph, my log e to the x plus 1 graph, note that that's a that graph there, e to the power of x minus 1, is e to the power of x, and it's been shifted down one place. Okay, so the normal asymptote of e to the x is the x-axis, but it's been shifted down one. So if we look at its domain and range, so look at that, its domain, there's no restrictions on the domain, it's all real numbers. Its range is from negative 1, not including negative 1, to infinity. Now this brings up something you may have realised already, that the original and its inverse, the domain and the range swap. So the domain of the original here is the same as the range of the inverse, and the range of the original is the same as the domain of the inverse. And pointing out again that symmetry, sorry, not symmetry, that reflection, I should say, across the graph of y equals x. Next one. Now I want to introduce you to some more terminology here. So when you're dealing with f of x, we might have mentioned this earlier, I'm pretty sure we did, then the inverse is f minus 1x. Okay, so that's the terminology when we're using function notation. So it says here, draw a graph of f of x and its inverse f minus 1x, or the inverse of x. Alright, so once again finding the inverse, and this can be done in the calculator. Let's work through the steps. First step, swap x and y over. From then on, our aim is to get back y back by itself again. Next step, take negative 1 to the left. Next step, undo it out of log form. So e to the power of x plus 1 equals y plus 1. Last step, to isolate y then, we need to take that plus 1 over. So we get e to the power of x plus 1 minus 1, and that's our inverse. And we're going to graph those two. So let's look at the original. It was log, the original was log x plus 1 to the base e minus 1. That's the original. The inverse, Okay, it's e to the x plus 1 minus 1. That's the blue graph there. Once again, I've drawn the axis of symmetry. I don't think it said to find domain and range this time. It didn't, but you could do the same thing. Remember, the domain of one is the range of the other and vice versa. It's a good one, once again, to see that reflection of the two graphs across that line of y equals x. See it there and there. Okay. All right. On the next slide, I'll get some problems for you to do. Finally, you can pause the video here and have a look at the questions I'd like you to do, especially those people away today on the athletics. Basically, if you watch the two videos on inverses and do these questions, you've caught up with things. So, good luck on the athletics, by the way, guys and girls. That's all for now. 11 minutes. Time to stop.